Good morning, everyone, and thank you, Altair, for hosting me here today. First, I have to apologize for my voice. I hope you can hear properly. My name is Carlo Pestelli. I'm from Bartila, and I am Senior Noise and Vibration Manager. And I have to deal with a lot of data, and I will explain something of what I'm doing. Few words about Bartila. Bartila is a global leader in maritime and energy markets. We have a full portfolio of products to support our customer in this business, but especially one of the core products that we have is the engine. And this is what I will talk about today, a specific component in the engine design. I would like to change the title of my presentation in Are You Ready to Burn the Ships? Why I say that? You might know that 500 years ago, Cortez went to the New World and he burned the ship as he reached, because the message was there is no way back. So now that we are entering the new digital revolution, there is something that will not be anymore like it was before. Let's see together. So, I was said I'm going to talk about two engines and a specific component of the engine that is the crankshaft. The best characteristic that we have to calculate in the shaft design is the torsional vibration. And I can assure you that simulation model reached a so high precision level that simulation and measurement are matching very well. But, you know, in real life, strange things happen. So let's think about what we can do about it. First of all, as engineer, we have always to deal with approximation. For example, we work with theoretical material versus real material. We deal with perfect excitation to apply to the system versus real complex excitations. Then, for noise and vibration, we typically work in frequency domain and is fine for most of the time and is very computational fast, but sometimes to catch some specific phenomena, we need to go to time domain. Then, most obvious, usually we validate components in laboratory controlled condition. That is very different from real life operation of our systems. Another interesting approximation is that we usually think in terms of deterministic approach. We think that what we apply to the system is reality, but the reality is more statistic than deterministic. Okay, so probably last century design approach was collect some data that we suppose are the condition, worst condition that could characterize the system, and we use this information to design, and then the system will go to operation, in this case, a ship. So let's start to burn our ships. First one, regarding the material, the most simple approximation of a material is the resistance to stress. Okay, but what if we could model the material to have a damage accumulation model for the material? This will open a new scenario for us. Then, second one, if we have a material that can accumulate damage, meaning a model that can accumulate damage, we could look at damage accumulation instead of stress level on a component. And this is very more informative because simply the damage accumulation, the fatigue phenomenon is exponential. So as soon as there is a little bit more stress, there is much more damage. So this approach allows us to look at the more stressing condition. Then let's suppose that we have a ship that is a ferry going back and forth between two cities. So we collect statistics of some ships ferry, and we see which are the conditions they operate more statistically. So we can add this information, this data, to our design approach. And if you do that, we see that opens a new condition that may be more stressful or more interesting to look at in the design phase. So, and as we can call, what to do today is so-called data-driven design process. So we design based on information collected from the field of similar ships and similar engines. So then what we can do further, thinking uh, about which data can we collect more, what we can do with this data. And that comes a concept that you might be familiar with. It's called digital twin. Okay, there are various interpretations of this wording. I want to specify my own. So, digital twin is a simulation model of a physical twin and has two important characteristics. And the first one is that simulation time is even faster than reality. So that can be more useful. Okay, so this is not a simulation model that takes 1 hour to calculate. It needs to calculate what is happening faster than how it's happening. Second characteristics has to exchange data, at least from the physical twin, and even back to give some reaction. So these are the two characteristics that for me define digital twin. With this approach, we are thinking at, let's call it a branding virtual sensor. So by fact is a digital twin application. So a virtual sensor is the idea of what if I could have a sensor where it's very difficult to place a sensor in a commercial application. Maybe in laboratory you can do it, but in a real operation condition, it's too complicated or too expensive or not lasting so long. So can we calculate that information based on other information instead of having a sensor in that place? That is the concept of virtual sensor. So to allow that, especially noise and vibration, since we need a very high frequency sampling rate to catch the phenomena, we would not be able to go for cloud computing. So we could not transfer our data fast enough to the cloud and have a computational model in the cloud. The best way is to do what is called edge computing. And that's so calculation right on the edge. Very simple. So what did we do? We took a computer with a simulation model on it, very simplified, very optimized. We are acquiring real data from our automation system, information that are fed real time to the model calculates the information. Of course, we can acquire also other information for comparison and understand deviation of the model and many other things that we can do. But in this way, we can place virtually a sensor everywhere in the shaft. Okay, instead of just one sensor, we can have hundreds of virtual sensors that are calculated real time or even faster than real time. So it's more useful information. There can be more strategy to do that. For instance, acquire combustion curve to apply the load on the cylinder. In this case, we adopted another model to simulate the combustion as well. So what can you do now that you have this information? The stress everywhere in the shaft. Using the accumulation damage model that we were talking before, what we can do is to look at how the shaft in every single point is accumulating stress. So if the real operation condition, some misfiring condition, some overpressure happening, some strange condition that the ships happen during operation are recorded and effect is added to the model. So this is just one example. So condition maintenance could be an example of how to use this digital model. Is this reality or fantasy? How? Now I show you a video. We are comparing now calculation to measurement. This is a ship that is doing an acceleration and the engine is doing from 300 RPM up to, I think, 600. And as you can see, is going through resonances. And below you have the comparison of time domain, so strain gauges versus virtual sensor. Um, and I think you can see with your eyes that today this approach is a reality. So now I'm just talking about calculating the value, not how to use it. Okay, as I said, you can use it in a simulation model or in a reaction way. Think about, for example, that when the engine was passing through a strong resonance, we could adapt real-time the combustion when the sensor was sensing so high stress and change combustion and destroy this excitation. Okay. So let's go a little bit forward. So this virtual sensor concept, application of the digital twin, um, is also a nice way to think that what is changed. What is changed is that the job of an engineer that usually was finishing in the design stage, in the validation stage of system or machinery, now your job is living with the engine or with the machine forever. So I think this could make you feel very proud that what you do is not ending in the lab. And this is clear giving whatever value to the customer. This is, I think, the business model are infinite possibilities of how to apply this and give more value to the customer. Could be predictive maintenance, could be optimization in real time for particular situations, you name it. So, and this, I know we're discussing about burning ships. So think completely different way of design. So what we could look forward is what we can call adaptive design. Not anymore design supposed on data or statistical data driven design, but create a design that adapts in real time to the condition. So this is what is possible to start to think today and look today. As you can imagine, now on the PowerPoint could looks easy things to do, but you have to deal with a lot of data. First of all, you have to measure data, acquire data, you have to organize data, you have to store data, you have to process data, and you have to use data. So in all this long data flow, I noticed that Altair can provide you a solution. So for every single step. So that's why I'm very proud today to give this presentation to you. So just brief recap. Did we burn some ships today? As I was discussing before, we can increase complexity today. So we don't have to think to keep the stress level below allowable stress because now we can even overstress a system, but think in terms of times of continuous operation instead of hoping infinite and then something strange happen. So as I said, we can go from looking at stress to look at the damage. And this, I think it will change a lot of way of thinking and possibility of what you can do with that. Once upon a time, we say we were designing for the more damaging condition. Now we can design for mission profile. That is happening already in aerospace industries, for example. But I think last line is the more fascinating. So from simulate for validation or optimization, we simulate to operate. So we simulate what is happening in real time to adapt and optimize the condition and the reaction of the system to it. Okay, that was all for today. I hope you enjoy the rest of the event, and thanks again, Altair, for the opportunity.